Okay, here we go. Today is Monday, April 16th. What we're working on today, the important bits, is working on LeChatlier's principle. Now, usually the discussion about LeChatlier's principle takes a long time in class because there's questions and feedback. So if you don't get this concept, rewind it and come back, okay? We're going to do it in 4 little segments that I'm going to talk about. Because it takes so long in class, I usually wait to do the demos until tomorrow, until Tuesday. All right. Wednesday this week, we're doing the ACT practice again, so we'll work on that. Thursday, we're going to review with using the review guide, and then Friday is the test for LeChatlier's for equilibrium and LeChatlier's principle. Okay, everything from the Pop Beads lab on. All right, we're going to start out with defining what LeChatlier's principle is. Henri Louis LeChatelier was a French chemist. Sometime about 1884 is when he was doing his work on his principle. Basically, what he was doing was he was investigating equilibrium reactions. He wanted to know what happens. He wanted to know how to predict what would happen if he applied a stress to a chemical system, to a system that's in equilibrium. And what he discovered is if a stress is applied to a system at equilibrium, it will shift in the direction that relieves that stress. Okay. A stress is defined as any change that upsets the equilibrium. And like I pointed out, there's 4 basic things that are going to happen. You can change the concentration, you can change the pressure, you can change the volume, and you can change the temperature. Pressure and volume are highly related. That's why there's a slash between them instead of a comma. The basic summation of this is if you do something to a chemical reaction, it's going to try and undo it. Kind of like if I pushed on a student, pushed them right in their desk to try and push them out of their desk, they're going to lean left to try and stay at equilibrium. They're going to try and stay in balance. All right. Let's start out right away with it and talk about how changes in concentration affect things. I find it useful to talk about this particular reaction. It's a very generic reaction. Chemical A plus 2 of chemical B in a reversible reaction can form chemical C and 3 of chemical D, 3 molecules of chemical D. The way I like to talk about this is a fairly direct way. I just like to talk about it in terms of what happens if I change something. So for instance, well, let me do it this way. If we say that we're going to, oops, got to get my pen out and hide that. All right. If we say that we're going to take A and we're going to increase our amount of A, the chemical reaction now has way too much A in it. Okay, so we're kind of imagining a situation where we've got a beaker initially that's full of this, and it's a chemical reaction that's at equilibrium, so it's going forwards and backwards at the exact same rate. So we've got some A, we've got some B, we've got some C, and we've got some D in a 1 to 2 to 1 to 3 ratio. Now, if I take another beaker that's got A in it, I pour this into the chemical reaction. Now my beaker that contains the chemical reaction that was at equilibrium isn't at equilibrium anymore. Now it's got a whole bunch of A, a bit of B, and a little bit of C and a bit of D. What the chemical reaction is going to do to change that is it's going to shift the reaction to the right. Okay, I'm only going to write shift to the right once. Usually we only write the arrow and we pronounce it as shift to the right. Okay, what does this mean that it's shifting to the right? Well, what it means is that the amount of C is increasing. Okay, so C increases. D also increases, and the way that that's being increased is it's taking A and B, and it's actually decreasing both of them because it had too much A. It's going to get rid of B to make some more C and D. That way its equilibrium comes back pretty close to what it was previously. Okay, now that hopefully wasn't too difficult to understand. Let's see another example here. What happens if I increase C? So we got to return to the original example. I've got a beaker that's at equilibrium. I add chemical C into the beaker. What's the reaction going to do to try and undo what I've just done? That's right. It's going to shift to the left to undo what I've just done. What that means is that it's going to decrease C and D because it takes C and D to go backwards to make A and B. All right. Ooh, that's okay. That's odd. Sorry about that. In order to make B and in order to make B and A, it needed C and D. So if it's decreasing C and D, that means it's increasing A and B. Okay, and the effect was made by the fact that I gave it too much C. Hopefully that was fairly predictable. Now, if I change the concentration of, let's say that I take B and I remove B out of this chemical reaction, what's going to happen to the reaction now? Ultimately, what we've done is we just crossed out B. We don't have any more of it. The reaction is going to want to try and make more B, so it's going to shift to the left. That means that A and B are both going to increase as this happens, and C and D are going to decrease as this happens. Hopefully there's no big surprises there. There's only one other thing I can do. Notice I increased the reactants, I increased a product. I decreased a reactant. I can also, decrease a product, like that. I can remove D. Removing D, the reaction is going to want to fix that, so it's going to want to make more D. That means it's going to have to shift to the right, which means that C is increase, and D is going to increase to fill that hole that we just made. That means that A and B are getting used up in order to make that C and D. Hopefully that makes some sense. Okay. All right. Some examples of this. Well, here we go. We just did some examples. So take a look. What happens if I increase the amount of carbon monoxide in this particular reaction? That's right. Shift to the right, because too much carbon monoxide, it's going to want to make more of the CH4 and H2O to get rid of some of that carbon monoxide. All right. This particular reaction, same exact reaction, only now I'm taking away water. There's a bit of a hole on the right side of the equation there, so it's going to try and fill that hole. So that's going to increase to the right. It's going to shift to the right. Same reaction, only I take away the carbon monoxide. Yep, that's a shift to the left, because now I've got a hole right here. It's going to want to try and fill that hole. The only way to fill the hole is to take methane and water and make carbon monoxide, as well as some extra hydrogen. That's a side effect, is that we get hydrogen out of this. And the final thing we can do, we can add some water here. And if we add some water, that means it's going to shift to the left, because now I've got too much water, it's going to try and get rid of it. Right. Halfway through, that's about half of what we needed to do. Changes in volume. All right. Changes in volume only apply to gas molecules. That's because solids and liquids are not, and also aqueous items are not compressible. What does that mean? Well, we can't compress them. Think about it for a second. Can you take a large block of ice, a 5-pound block of ice, and can you compress it down into the size of an ice cube? That would be ridiculous. Also can't do the same thing with a fish tank full of water. We can't compress it to the size of an ice cube because it just doesn't work that way. Liquids are not that compressible. On the other hand, gases are extremely compressible, and they will compress down to very, very small sizes compared to their previous size. For instance, the amount of gas that's contained in a propane cylinder, like the kind that's underneath a gas grill, probably is going to take up about as much space when it's not pressurized as an auditorium. A note here. When we change the volume, we're also going to be changing pressure because the two are intrinsically linked. You need to think about a balloon that's being held in your hand. Okay? If I decrease the volume of that balloon, that means that I've got my hand on the outside of it and I am pushing on both sides of the balloon, maybe even all sides, if it's a small enough balloon to fit my hands. Okay, so that means that the volume is going to decrease But now the pressure inside of the balloon is much, much bigger. The pressure inside the balloon used to be pretty small. Let's put it that way. But now the pressure inside the balloon is much, much bigger than it used to be. So a decrease in volume means an increase in the pressure. Let's go through some examples of changes in volume. This is going to be a decrease in volume or an increase in pressure. So again, it's the balloon example. This particular chemical reaction is happening inside of a balloon, inside our hands. What we're doing is we're allowing it to come to equilibrium, and then we're going to push on it. What's going to happen with this chemical reaction? Well, it turns out that what's going to happen with the chemical reaction is that it's going to favor the side that takes up less space. If you look at it here, you can see that there's 1 mole of carbon monoxide and 3 moles of hydrogen. That's a total of 4 moles. There's only 1 mole of methane and 1 mole of water over here, so that's a total of 2 moles. We call them molecules if we want, so 4 molecules on the left and 2 molecules on the right. If we make the space smaller, which one is going to be easier to store? 4 molecules or 2 molecules? Turns out the answer is pretty easy, right? 2 molecules are easier to store, so this reaction is going to shift to the right because of that. Again, it's because there's a decrease in space available. These 2 molecules are what's favored because it's a smaller amount, so we're going to shift in that direction. Now, on the other hand, if we were to decrease the pressure, so we let off of the balloon, it's going to increase in volume again. Same exact reaction, but now it's going to shift the other direction. Because it's got the increased volume, it's going to have the ability to take up more space, so more molecules are going to be favorable. We're getting through. 1/3 of it all done, or 2/3 of it done, 1/3 to go here. Changes in temperature. It turns out, and this is the most important part, the only way to change a KEQ, an equilibrium constant, is to change the temperature. That's why all of those equilibrium problems that we've been doing have got the temperature written on them, because the reaction only has a KEQ at a very specific temperature. You've got to recalculate at different temperatures or look it up again at different temperatures. Okay. Now, I don't like much the way the book talks about KEQs with temperatures, so here's the easy way to deal with this. The easy way to deal with this is to think of temperature the same as any other chemical that's in the reaction. To think of it as if it were a concentration. Technically it's not a concentration, but it gives you the right answer every single time. So, for instance, if I increase the amount of water here, that's going to shift the reaction to the left because it's want to get rid of the extra water. Now, this reaction has heat in it, so if I added more heat, it's got extra heat it wants to get rid of. That means it's going to shift the reaction to the left to get rid of that heat. On the other, what that means, there's a very interesting thing that's going on here. We have to talk about the KEQ, okay? What that means as far as the KEQ is concerned is that it's making more reactants, more stuff on the left than it is products. So that means that when I write products over reactants, products is very small and reactants are very large. When I take a ratio like this, a small number over a large number, I get a small number. So what winds up happening here is the KEQ actually winds up being reduced as it shifts left. And remember, temperature changes are the only time that that's going to happen, that a KEQ is going to change. If we look here, a loss of heat, there's basically a hole here. It's got to try and remake that heat. So the reaction is going to shift to the right. The KEQ over here, as this reaction is making more products, the size of the products is large, and it's decreasing the reactants, so the reactants is going to be smaller. What that means ultimately, a large number over a small number, it means the KEQ is going to be increasing in size. So the KEQ has gotten bigger than it used to be previously. We can predict that it's bigger. As far as how much bigger, we're not going to be so concerned about. Now you can see both of these reactions are exothermic reactions. There are endothermic reactions that have heat at the beginning. We want to take a look at this kind of reaction because if we take away heat from this reaction, it's a little bit different than before. Notice taking away heat here shifted it to the right because there was a hole over here. Now there's a hole on the left side if we take away heat, so it's going to shift the exact opposite direction. If we analyze the KEQ though, what we're going to notice is that there is something predictable here. A shift to the left and a shift to the left mean the same thing as far as products and reactants are concerned. A shift to the left means I'm making more reactants and less products, which means that I'm going to have a decrease in my KEQ. Finally, this reaction here. Okay, so with this last equation here, what we're seeing is that the heat is being increased. That means there's too much heat over here. That means we're going to shift to the right. As far as how the KEQ gets affected here, let's take a look. KEQ of something that's shifting to the right, well, the right means you're making more products. So products are big, reactants are small. That means that your KEQ is going to be relatively large. Large number over a small number. Okay, so KEQ is actually increasing with this. Just as a quick recap, temperature is the only thing that can change a KEQ. Last bit. We're going to use this equation to answer these last few questions just to make sure that you understand the concepts. These are the tricky ones. The question is, with this reaction, where heat plus A that's a gas, plus 2B that's a solid, plus C that's a gas, plus 3 of D that's a liquid. What happens if I increase B? Take a quick moment to think again. B is a solid. Do solids affect equilibrium constants? Nope. Are they concentrated? Am I actually increasing the concentration by adding any of B? I'm not. This reaction does not shift because solids and liquids don't affect a KEQ. That means they don't affect a Q either, which means they don't affect this reaction. Let's try an increase in pressure. Take a look at that, see what an increase in pressure is going to do. Now remember again, the only thing that matters in a pressure is a gas because solids and liquids are not compressible. So if I ignore my solid and my liquid, I've got 1 mole of C and 1 mole of A. Neither one are higher than the other, so there's no shift here because we have an equal number of moles on each side. All right, the final question here, what happens if I What happens if I add a catalyst? Okay. Catalyst. Okay, so what happens if I add this catalyst? Catalysts don't affect a reaction rate. Catalysts do affect a reaction rate, but they don't affect a KEQ. So there's going to be no shift here either. If I add a catalyst, that means that it's going to go to equilibrium quicker. It's going to shift colors quicker. If I'm using the milk of magnesia demo as an example, it's going to shift colors much quicker with catalyst than without. But nothing's going to happen. It's not going to affect the way it shifts. It's still going to turn purple. Okay, that's it. We're done with that. So if you had questions, probably go back and take a look at the video one more time. And you should be able to fill out the LeChatlier's principal worksheet. Now there are 3 sections on it. My suggestion is this. Learning is done best with repetition. Let me say that again. Learning is done best with repetition, especially this one. So my suggestion is do the first section and check your answers. Then come back and do the second section and check your answers. Then the third section and check your answers. I'd say to give yourself a couple of hours at least in between, maybe even a day's break in between each of those 3 sections. Okay, that's about all that I've got here. So good luck.